called the representation theory of Hessenberg varieties.
All right, so thank you. It's a pleasure to be here. So I'm going to be talking about the representation theory of Hessenberg varieties. And broadly speaking, the talk is going to have three parts. I'm going to start by actually just talking about Hessenberg varieties, defining them, describing them, giving a little bit of their geometry and their context, and then talking a little bit about the representation theory associated to Hessenberg varieties in particular, and some other related varieties, and then finally talking a little bit about some more recent results and open questions around, specifically around some of the representations that we'll see. So, all right. So for the first part, okay. So for the first part, Hessenberg varieties are a family of varieties. They sit inside the flag variety. So depending on how you like to think about the flag variety, you can think about it as this quotient, say, of a linear algebraic group, complex reductive linear algebraic group G by a Borel. You could, and for parts of this talk, it will be essential to think about it as, say, GLN with complex coefficients modded out by specifically upper triangular matrices, or you could think about it sort of Fulton style as the collection of flags in which we think about these sort of like nested subspaces of complex vector spaces. So each PI is some I-dimensional complex vector space. And they're nested inside of each other all the way up to some sort of fixed ambient n-dimensional complex vector space. So we'll take all of these viewpoints at different moments. The first thing that I want to do is so Hessenberg varieties in general have two parameters, and we're going to start by thinking about one of those parameters, and then we're going to throw another parameter in there. So the first parameter, I want to take x to be some element of the associated Lie algebra, or over here, I'm just going to think of x as some n by n matrix. Okay. So right now I'm going to be giving you a whole one set of family of Hessenberg varieties called Springer fibers. Springer fibers, loosely speaking, are the flags fixed by a specific x. So more precisely, given some x, so I'm going to call it sort of curly s x. The Springer fiber associated to x is the collection of flags such that x sends the ith part of the flag back to itself for all I. Or, if you prefer, you can rewrite this condition. Just thinking about it as the collection of flags, such that the adjoint action of G on X sends you back into the Borel, makes you upper triangular. So, okay. So these are the flags fixed by X. That means, in principle, that if we change X, this should change also. So, for instance. Let's just walk through this in a couple of cases. So if I pick x to be 0, then then 0 sends everything to 0, which is always inside vector subspace. So the Springer fiber associated to 0 is the full flag variety. Now, if I pick some other x, let's see. So any other x, in fact, let's let's look just at this particular condition right here. X sends the line back into the line. So this actually tells us in general that we should think of V1 is spanned by an eigenvector for X. So this means there's actually like a whole bunch of different matrices for which this is essentially the only observation we need to determine the whole Springer fiber. Like for instance, if I pick something like this, principal nilpotent or regular nilpotent, one single Jordan blocks. So this has only this one eigenvalue 0 and only this one eigenvector, just like your first standard basis vector. But at the same time, if you sort of quotient out by the line spanned by that eigenvector and look at that condition, x v2 goes into v2, you're going to get essentially the same argument. The plane should be spanned by the eigenvector plus the eigenvector for x inverse. And you're going to kind of keep running through this and see that there's only really one choice for the line, for the plane, for the 3 space, and that one choice is just the identity flag. On the other hand, if you pick something that's like regular semi-simple, well, now I have 3 choices for what the eigenvector are going to be, any of the standard basis vectors. Once I pick them, the plane is actually still going to be essentially spanned by 2 eigenvectors, so I have 2 choices left over, and so on. And I end up with n factorial permutation flags. So finally, okay, so there are different kinds of Springer fibers. I'm not going to go through this example, but I'm going to tell you. I'm going to assert. I'm going to assert that you could actually give this as a linear algebra exercise. You can sort of argue through using linear algebra stuff, and convince yourself that if you take a matrix, say, with Jordan form. That has 2 blocks, one of size 2, one of size 1. You get something that looks like this. So, so you get basically 2 copies of P1 glued at a point, and from there, I'd say, yeah, I mean, if we were using bigger matrices, you'd get all sorts of crazy stuff about which I'll say a little bit more a little bit later. On the other hand, there's one of the parameters that I wanted. I have this, say, linear operator x. I would like to have another parameter as well. So I'm going to think of this as a subspace of the Lie algebra. And I want to require that it be stable under adjoint action with the entire Borel. And for some purposes, I might also ask that it contains the Borel. So if I were thinking type A more concretely, I'd be thinking about something like this. So arbitrary entries above some staircase and 0 below. And if I wanted this parenthetical comment, then I would also say H contains all upper triangular matrices. So okay, that's just like working out what these conditions would mean in type A. There's another way that I can kind of keep track of it. Instead of keeping track of this whole subspace, I can actually kind of just record how many non-zero entries you're allowed in each column. So just like keeping track of it via a function from the integers 1 through n to themselves. Okay, so these are just different ways of encoding this second parameter. So for instance, here, 3 possible examples. All right, so I could take h of I equal to I for all I. So this would correspond to upper triangular. I could take h of I equals n for all I. This would correspond to, well, everything. And I could take h of I equal to I plus 1 for all I up to n minus 1. This would look like something where you've got all of the upper triangular things, and then you're also allowed to be non-zero just below the diagonal. So I just mentioned that because well, all right, so this is a subspace of the Lie algebra, but it's not parabolic. And so it is quite possible to pick these things to be not parabolic, and in fact, it's often most interesting to pick these subspaces not to be parabolic. So so our Hessenberg variety of x and h is really going to be essentially your Springer fiber, but add another parameter. So it's the set of flags such that x sort of is allowed to move the ith part of the flag, but not too much. It's constrained by the function h. So it has to move the ith part of the flag into the h of I part of the flag, or equivalently over here. So for instance, right? So for instance, with those first 2 examples. There. So when h of I equals I, our Hessenberg variety is just the Springer fiber again, because we're just saying that x sends the ith part of the flag into the ith part of the flag. When h of I equals n, so in this case, we're saying that x sends the ith part of the flag into the entire vector space. So that's also trivially satisfied. So that recovers the full flag variety, regardless of what x was. Now, this third example. So this third example. So this third example is just like interesting and more complicated, and I want to give just one more example, so that we can kind of see it being interesting and an example and more complicated, just to sort of see what kind of phenomena show up here. So I'm going to pick. Let's see. I'm going to pick a fairly simple x. Okay. I'll pick another so regular nilpotent x one more time. And here's the thing that we're going to sort of look at. So we're going to look at what this condition says just for the line. So we're saying that x sends the line into the plane, and in particular, if we have any old vector that, let's say, spans, it's going to be the vector that spans the line. We can see, just because I wrote down the matrix multiplication, we can see that x sends this vector ABC to this vector 0AB, and once we've done that, we can pretty much convince ourselves. So let's see. As long as either A or B is non-zero, these two vectors are linearly independent. X has to send the line into the plane. So I've got two linearly independent vectors that have to be sitting inside the plane. So in fact, the plane is going to have to be spanned by these two vectors. All right. So what am I saying here? So if A or B not equal to 0, then so those two vectors are going to span V2. So let me kind of just enumerate some of the possibilities. So it could be that the first vector we picked was 1, B, like so. In which case, x is going to send that to 0, 1, This is going to be, I'm going to write this down as the vector that spans V1. These two span V2. Well, those three are going to span the whole space. So this tells us this is like one whole family of flags that are contained inside of this Hessenberg variety. On the other hand, I could have picked A to be 0, in which case I have something like this. And if I'm just looking at three-dimensional flags, then I really only have one choice to fill it out. If A and B is both equal to 0, or if A and B are both equal to 0, then C has to be non-zero. And I have a couple of other choices. Well, actually, now I'm sort of like stuck in a smaller dimensional version of exactly the same argument. I'm going to have like two basic choices for how to complete these flags. So kind of counting through all of the options. So this is what the Hessenberg varieties look like in this case. So these are also called Peterson varieties. And you can actually construct the quantum cohomology of the flag variety using them. That's why Peterson was thinking about them. But they're also a smaller piece, and not what we're going to talk about for most of the time. So what I want to do, having sort of introduced what these things are, let me just make some sort of general comments about geometric properties. So geometric properties in general, things that I can say about Hessenberg varieties in general. So one is, well, they can be fairly complicated, but they're paved by affines. So they don't have a supernatural CW structure on some level, but they have like the next best thing. You can slice them into affine pieces so that the closure of each affine piece is contained in some union of smaller indexed affine pieces, not necessarily smaller dimensional, but smaller indexed. So you can kind of see the difference between a paving by affines and a CW structure right here. So I don't have that one point on the pink cell. So in a CW cell, CW decomposition, I'd want the closure of each cell to be a union of smaller dimensional cells. That doesn't happen here. I'm picking up like 1 point off of this green piece. On the other hand, from the point of view of certain kinds of like topological invariance, this paving is like telling you exactly how many Betty numbers you have and where they are. So it's better than a CW decomposition from some point of view, simpler. So that's true in general. Hessenberg varieties are paved by affines.
Did you say affines mean affine spaces?
I mean like affine spaces, not affine varieties. These are like, right, yeah, actually isomorphic to c to the k for some k. And, right, right, something that you can actually kind of see in some of the examples here. So if you set everything up in the right relative positions, these affines are intersections with Schubert cells. All right, so you can totally see that in that example right there, because your classic way of sort of like writing a Schubert cell inside the flag variety, if you're writing them out explicitly, is as a permutation with non-zero entries in certain locations. Depending on your conventions, we're kind of using above ones and to the left of ones. You can also see that we're cutting just certain slices out of the Schubert cells. Generally, you would allow sort of arbitrary entries, but you can see in that top left cell, 2 of those entries actually have to be the same. So there are conditions going into those entries, and they get more and more complicated the bigger things are. So if you think about Schubert calculus, you can actually ask, you can ask all sorts of analogs of Schubert calculus type questions. So a lot of thought has gone into what to say. So a lot of thought has gone into the geometry of Schubert varieties, and partly because it is just inextricably linked to the combinatorics of the permutations that index the Schubert cells. So things like the dimensions are dimension of Schubert variety is the number of inversions of the permutation. But even sort of more complicated statements around when things are singular is linked to certain kinds of pattern avoidance within the permutations, and so on. So if I were to just like write down in, I don't know, 60 seconds or less, key kinds of questions, you could ask about the dimensions of these cells. And let me just like say, yes, that's like pretty well understood, and it's understood as certain inversions that can be combinatorially characterized for the permutations that index the cells. You could also ask questions like, right, you could ask whether these cells are like whether these varieties are equidimensional. And so now my answers are going to get less satisfying because, like, not always here. So Springer varieties are equidimensional. It's sort of like classical result of Spaltenstein's. But some Hessenberg varieties are not. We don't actually have a nice closed description of like when they are equidimensional and when they're not. You could ask about closures. So closures of your Schubert cells, are characterized by the Brugger order on permutations. So just by virtue of being paving by affines, we're not exactly going to have closures in the classical sense. But you could ask, for instance, like which permutations are in the closure of which of these affine pieces. And very little is known outside of the Springer case with some work of Fress and Melnikov. Also, you could ask about singularities. So when are components singular? When are they not? And again, sort of very little is known outside of the Springer case. Also some work of Insko and Young. It's sort of like in special cases. But again, the places with the answers that we do have, we see similar phenomena to Schubert calculus in the sense that they're sort of like encoding combinatorial and then sometimes representation theoretic properties in their answers to these questions. All right, so that was like part one. So now we're thinking about representation theory and how we get representation theory associated to these varieties. And so representation theory associated to Hessenberg varieties. So I'm actually going to start. I'm going to start actually with the Springer case for a second, because it's going to tell me a story that actually doesn't generalize at all, but I can still wave my hands and say it's like close enough on some level. So Springer fibers. So Springer fibers were like identified first and identified precisely because of their representations. So the cohomology of Springer fibers carries an action of the symmetric group. I mean, you can kind of see it even just on the level of this particular Springer fiber right here, because I've got n factorial permutation flags, and like I can define a permutation action right there. So the sort of even more interesting parts is that when X is nilpotent, the top dimensional cohomology of the Springer fiber is an irreducible representation. Okay, so this is like a little bit more surprising, partly because, like, actually, if you look at this variety right here, which is associated to a nilpotent element, it doesn't actually have any obvious like permutation action on the level of the variety, because in fact it doesn't have a permutation action on the level of the variety. But nonetheless, the cohomology has a representation. The top dimensional cohomology is irreducible, and as you vary over conjugacy classes, of nilpotent X, you recover all irreducible representations of Sn. And we can actually, well, so we can't exactly see it, but we can numerically convince ourselves that it's plausible. Over all of the conjugacy classes is the same as saying over all the Jordan types. Here's one, here's another one, and there's a third one when n equals 3. So there is like one top dimensional cell for the full flag variety. So we should have one rank 1 irreducible representation. Here is a point, so it also has just one top dimensional Betti number, and here this one has 2. So what we're recovering ostensibly from this theorem is that the irreducible representations of S3, they should come with one rank 1, another rank 1, and another one rank 2, which is true. So encoded right there in the geometry as well. Great. So I'm not going to prove this construction. Actually, I'm not going to say. I'm not going to prove anything, but I'm going to give you a picture that maybe at least shows you one possible way of constructing the Springer representations. There are like a million different constructions of the Springer representations, from very concrete to very abstract. I'd say every single one of them is hard in one way or the other. Like if you go for a more elementary description, then you use like a lot of sweat to get there. And if you go for a less elementary construction, then you use like a giant machine to get there. And so there's like there's no way of just doing it easily. Also, I guess just as an aside, there's no consistent description of exactly what the Springer representation is. It's either the thing Springer described or that thing tensored with the signed representation. But pretty much we just agree that if you've constructed something very similar, then like it counts as a Springer representation. So depending on what you find, it might vary just a little bit by convention. But let me give you a sort of picture. The kind of Grothendieck's picture for sort of roughly what's going on. So what I'm going to do is I'm going to think about, let's think about pairs of a Lie algebra element and flag. And I'm going to think about specific pairs. So I'm want to think about specifically those such that G inverse xg lands in the upper triangular. So that's the condition that I've been writing before. And I am going to think about just mapping down to the Lie algebra by just forgetting the fact that I have a flag there. So what would I say over here? Well, I could say, so the fiber over this map is, in fact, the Springer fiber. So that's where the fiber in the name comes from. It's the fiber over here. G, I guess another thing that you could say is if we kind of instead thought of like forgetting about the Lie algebra element and just like map down to the flag, you could convince yourself that this is a resolution also. So now I'm going to look at two different pieces. So one of them, I'm going to look at the regular semi-simple elements and distinct eigenvalues, let's say, and just look at what happens up here. Well, we kind of already figured out in one completely representative example. Okay. So in this case, which is kind of like this is like the generic case, most matrices are regular semi-simple. We have n factorial permutation flags sitting around upstairs, and so we can kind of just see there's this sort of like natural permutation action that's just like it's just acting as deck transformations, permuting these different n factorial different permutation flags as we move around over there. All right, so on the other hand, we can restrict to the nilpotent matrices, the nil cone. Over on this side. So when we do that, so like right, so on the right hand side, Sn acts on the fibers. On the left hand side, so that particular that resolution of the nil cone is also has other really great properties. In particular, it's a semi-small map. So that's a condition relating the sort of strata, the conjugacy classes down below, the codimension of the strata to the dimension of a pre-image. So sort of to confirm that, you actually need to know something about the dimension of Springer fibers to be able to count the dimension of Springer fibers given a particular x. But once you have that, so the decomposition theorem, speaking completely informally, it pretty much allows you to kind of take the representation in the sort of generic situation and kind of slice it, where it says that the representation that representation moves over onto the nilpotent part, and really sort of like more counting arguments around the sizes of the Springer fibers that tell you that really only this sort of representation on the regular semi-simple part so that is the whole thing that determines the Springer action. Okay, so that was intentionally vague and more alluding to some results than actually exactly telling you what they were, but kind of telling you certain key points so that I could say, there's sort of similar ideas work for Hessenberg varieties, but not exactly. So not exactly in the sense that if you tried to change this central map and just replace the Borel by, like, say, an arbitrary Hessenberg space, then this map over here would just change its size and it would no longer be semi-small. So the left-hand side map isn't semi-small. So you need to do more sort of counting or other things to kind of fix that problem. On the other hand, however, the sort of Hessenberg representation is still completely determined by the regular semi-simple part. So by whatever sort of action you have above the matrices that look like this. And that I can make a little bit more precise when I say it's determined by that. So in the following sense. So for instance, I'm going to write a whole bunch of symbols and tell you what they all are. All right, so I'm going to take a Poincare polynomial of a Hessenberg variety. A Hessenberg variety of a particular H and mu. All I actually care about is the Jordan type of mu. I don't need the specific matrix. So these are sort of Poincare polynomial of the Hessenberg varieties. And then over here, I start with this. So I'm going to peel off. So I'm going to sort of look at the action on the regular semi-simple part, and I'm going to peel off for each irreducible representation. I'm going to peel off the sort of lambda isotypic component. And I'm just noting this comes with some grading, so that's what Q is recovering. And then finally, I've got some coefficients here. And my coefficients are certain kind of normalized Poincare polynomials, which show up in combinatorics of Young diagrams a lot. Say that again?
Still looking at representations of symmetric group?
So yeah, actually, that's a great question. So this is a place where, so this particular result, we do need type A. We use some things that are only known for type A. So this is still SN. Maybe also. So this is actually, I kind of gave this setup of the Springer representations. This really isn't this isn't actually the Springer. This is not the Springer representation. So I mean, in a significant way, right? Like, so permutations act on themselves either from the left or from the right. And so the Springer representation, you act on the right, and that just doesn't extend at all to Hessenberg varieties. So what we're actually looking at here is the monodromy representation, if you like that. The other piece here that I would say as a moral right up until this point is that these sorts of geometric properties and questions on the level of the Hessenberg varieties are really essential to get this kind of thing working. So it's like either hidden or front and center in various parts of this story. So, all right, okay. So then what I'm saying is that the representation here, just like for the Springer case, where like the representation over here is kind of this is a regular representation showing up here. So here we're saying, in general, in Hessenberg varieties, whatever representation you get on the regular semi-simple Hessenberg variety is somehow telling you a lot of information about this sort of larger picture. So I think the question is, like, what is the representation on the regular semi-simple Hessenberg variety? And I'm going to spend, I think, the rest of my time talking about this in two different ways. So first, I'm just going to give you a concrete description. So this concrete description is going to just use localization techniques in equivariant cohomology, not dissimilar to things that came up in the previous talk, right? So if X is regular semi-simple, so if you'd like, just think of it as diagonal with distinct values along the diagonal. So then the whole Hessenberg variety carries has a torus action. And that's not generally true for Hessenberg varieties, but it is when we're regular semi-simple. And so then there's actually like a machine that we can use. There's a machine that we can use to like say a lot about the equivariant cohomology in this case, because also we have things like a paving by affines. So some of the geometric properties actually just like allow us to use this other machine. So for formal reasons, coming from the geometry of Hessenberg varieties, the equivariant cohomology, right? So we have the fixed points sitting inside of the whole Hessenberg variety. And in fact, this induces an injection going the other direction from the equivariant cohomology of the whole variety. Oops, let's not be too confusing. All right, so there's an injection on the equivariant cohomology into the equivariant cohomology of the fixed points. And we saw in the previous talk, right? So the equivariant cohomology of the fixed points is just a polynomial ring. Or copies of polynomial rings, one for each of the fixed points. And we can actually we can determine the image from the one-dimensional orbits of T on the Hessenberg variety. So these results. So these results are well known. The whole sort of package is often referred to as GKM theory. It like applies for lots of other varieties than just the ones that I'm talking about today. But I'm just going to give it to you in this particular setting for convenience. And so All right, so then the way to sort of describe the equivariant cohomology in this case is to set up a graph where the vertices are the t fixed points, which in our Hessenberg case is actually just always all of the permutation flags. The edges correspond to one-dimensional t orbits, which in our case corresponds to situations where you have a permutation and another one that you get by left multiplying by a transposition. Subject to conditions on H. And then we have labels on the edges. So weights of the torus action on the one-dimensional orbit which we'll just write down as these differences, Ti minus Tj. So here, for instance, so here's what these graphs look like. Here's what these graphs look like in a couple, well, in all, essentially all of the different examples when n equals 3. And let's see, I've used different colors to label the edges, although they're a little bit hard to read, I bet, from the back of the room. Pink edges, which are the ones with sort of positive slope, those would be T2 minus T3, and green edges, which are the ones with negative slope, those are T1 minus T2, and then your straight vertical edges are the ones that are T1 minus T3. So the one on the right, combinatorialists recognize as essentially the Bruhat graph of permutations of the permutations S3. And great. I have exactly the right amount of board space to actually say what the permutation action is and what the equivariant cohomology is. So given the graph, okay, so what I have, a priori, I'm setting aside the equivariant cohomology of a bunch of fixed points. So I've got polynomial rings, one copy for each of the fixed points. So I guess I could even write this as n factorial different polynomials, such that for each edge, uv, labeled, let's say, alpha uv, we have a condition that whatever polynomial you have at u minus whatever polynomial you have at b is a multiple of that difference, is some multiple of the label on the edge. So like, for instance, over here, since there are no edges at all in the Springer case, there are no conditions whatsoever, and we just have n factorial copies of the polynomial ring, which is kind of recording the fact that we have n factorial distinct points up there in the Springer fiber. Over here, you have a ton of conditions, which is encoding the fact that the cohomology of the flag variety is actually kind of complicated. So this kind of, okay, there's the result. But maybe to say what kind of permutation action we get, I'm going to tell you just by telling you what each simple transposition does. sample transposition that exchanges I and I plus 1 acts by the rule so if you have one of these elements of the equivariant cohomology ring, and you want to act on it by SI, so then the thing associated to vertex U is going to be whatever you get by taking your original polynomial, so taking the polynomial that used to be associated to SIU and then acting on it by SI. So essentially, what I'm saying is that these conditions play well with certain kinds of application of permutations. This, by the way, I have written this result with a lot of type A dependence, but this is not a type A result. That's a general statement. So, all right. So, So I'd like to switch gears completely and say something that would be appropriate for a completely different conference. Because it turns out it is actually related to this kind of. So what I'd like to do right now is actually just move to a purely combinatorial question. So let me kind of, if you have never seen a graph coloring, take a combinatorial graph. And what you want to do is assign colors, which we'll think of as just integers, to the vertices. We're going to think about a proper graph coloring, in which case adjacent vertices have distinct colors. Okay, that's a classical thing to think about it's a classical thing to think about in graph theory, and there's a lot of work done on what the minimal coloring number is and what it looks like for different families of graphs and all sorts of things like that. So Stanley defined the chromatic symmetric function. And what he was really after was basically taking for a given graph, encoding information about like all possible graph colorings all at the same time. So that's what this chromatic symmetric function is going to do. I'm going to take a sum over all proper colorings, which I'm now just thinking of as a function from the vertices to my coloring set. And what I'm just going to do is record every time a vertex is colored a specific, every time a vertex is colored with a specific color. All right. So this is a symmetric function because if I just take a specific coloring and then like kind of permute the colors that I used, it's going to show up as another term somewhere else. So it is a perfectly good symmetric function. And then the Stanley Stembridge conjecture is that if this is a symmetric function, I mean there's a lot of different bases for symmetric functions, and so One is often trying to take a given symmetric function and, for various reasons, write it in terms of specific bases. So their conjecture is that this is positive in the basis of elementary symmetric functions. Meaning if we write this out in terms of elementary symmetric functions, we're going to get non-negative coefficients of all of those elementary symmetric functions. This also, I mean, I think their original conjecture, they were thinking about some sort of deep properties of maintenance. And you know, so people have thought about different like pieces of this. I think the conjecture, this is 1993. You are seeing, this is a sort of a version of it from Guay-Pacquet. But like other people had thought about pieces of this result in the interim. Heyman actually showed that chromatic symmetric function is non-negative in the Schur basis. And Goncharov actually gave sort of combinatorial description of what those coefficients are when you express it non-negatively. So nonetheless, this particular version this question seems to be hard because people keep not answering it. So more recently, Sheresian and Wax came up with something that sort of modifies this just a little bit more. So they call it Q-chromatic quasi-symmetric function. It is no longer, we're going to break some of the symmetry. So we're going to break some of the symmetry because what we're going to do is we're going to keep track of certain kinds of ascents. So we're going to do all of the same stuff. All the same stuff that I had up there. Okay, so that part is all of the same, but now I'm going to add another term, a Q term, that's telling me something about ascents on the coloring. And so basically, whenever, if you've indexed your vertices, whenever two vertices sort of have the same relative order in the vertex set, also have the same relative order in the coloring set, it's no longer symmetric because if you change the order of the coloring, then something could go from being an ascent to not an ascent. On the other hand, it's fairly close in some way that you could formalize if you wanted to think about quasi-symmetric functions. So they thought about this originally restricting to particular families of graphs. They originally thought about these graphs as certain things coming out of unit intervals, but actually they could as easily be described as graphs coming from these Hessenberg functions H, where vertex set is the integers 1 through n, and you have an edge where you have some edges characterized by conditions coming from this function h that end up sounding pretty similar to the kinds of conditions that I didn't use when I was describing how the graphs were formed over there. So the conjecture the conjecture actually is that So these polynomials are actually the graded Frobenius character of the SN action. On this permutation action right over here. And so that's sort of the Sureshian-Walk's conjecture. Which was just proven by Brosnan and Chow, and actually, within a matter of weeks, also proof announced by Guay-Pacquet. So basically two almost simultaneous and completely independent proofs, one of which the Brosnan and Chow result is really essentially geometric, uses the decomposition theorem. Not totally dissimilar to part of the things that we were talking about, and the other of which is like really combinatorial, uses Haupt-algebras, and analyzes the actions on those graphs. Pretty extensively. So just at exactly the correct amount of time. So this third piece. So what this third piece of the story is saying is that there's this kind of like big and vexing open combinatorial problem that's been open for a while that appears to be a strictly, straightforwardly combinatorial question, and yet that turns out to essentially be the same as a question about analyzing this particular geometric representation in a kind of more refined fashion. Moreover, there is a certain amount of optimism right now that because geometric techniques have actually already been useful right now, that it's a place where some sort of geometric analysis might prove to be more insightful or illuminating than the straightforward combinatorial techniques that have been applied in the past. So I think that's a very broad kind of open question of what people are thinking about with this particular question. Yeah, and I'll probably stop right there.
Are there any questions? So do you have this kind of positivity for Hessenberg varieties?
Well, so this positivity result. So it's equivalent to
helpful to know this interpretation.
Yes, because programming there's a company description in this case, and then frankly, I think part of the other thought is that all the tools that people have before are already formatted. So let's try some others.
What was the geometric interpretation culture?
It's more of the combinatorial. So it's more of a combinatorial like so. Heyman wrote those symmetric functions in terms of J functions, and then said, okay, so there's certain coefficients there, and Gotcha came up with particular feelings of handling if you think of as what were in those coefficients.
Do you have any questions? Well, let's thank the speaker again.